Today we will discuss different types of energy conversion that we frequently come across different devices. So let us take some examples. First example is a DC motor. A DC motor is a device that converts electrical energy to mechanical energy. It takes input as electrical energy and produces rotational energy of the motor. The motor rotates on getting electrical energy. So you can say that a DC motor converts electrical energy to mechanical energy. Electrical energy to mechanical energy. On the other hand, if we consider an AC generator or a dynamo, AC generator or dynamo. Now this AC generator consists of a coil which rotates in a uniform magnetic field, and therefore it converts mechanical energy. It converts mechanical energy to electrical energy. For example, if you consider a thermocouple, then thermocouple is a device which converts heat energy to electrical energy. This thermocouple is probably the only one example where we realize the conversion of heat energy to electrical energy. You will get several examples where electrical energy is converted to heat energy, but conversion of heat to electrical, a thermocouple and a thermopile are the only examples. Actually, collection of thermocouple is called as thermopile, and a thermocouple is made by a combination of two dissimilar metals. It is actually a combination of two dissimilar metals, such as copper and iron, where the junction of copper and iron is maintained at two different temperatures. Suppose this is a copper metallic bar and this is suppose iron bar. Suppose this is made up of iron and this is made up of copper. Then the junction of copper and iron, we will get two junctions of copper and iron. One junction is kept hot, maintained at a higher temperature, and another junction is maintained at a cold temperature or a lower temperature. Then we realize that current flows from hot to cold junction along copper to iron. So this will be the direction. You need not remember this because this is elaborately discussed in class 12, but for the time being, you can just remember that a thermocouple is actually a combination of two dissimilar metals, and it is the only example where heat energy is converted to electrical energy. You will get several examples where electrical energy is converted to heat energy. For example, a toaster, geyser, electric iron, and many more examples, immersion rod, etc. They all convert electrical energy to heat energy. Electrical energy to heat energy. Let us go through some more examples. Electrical to chemical energy. Suppose we charge a battery. If the battery is rechargeable, then definitely it can be charged. So charging of a battery is a process where electrical energy is converted to chemical energy. Electrical energy is converted to chemical energy. But when the battery is in use, when current is drawn from the battery, what we call as discharging of the battery, then the opposite happens, that is chemical energy is converted to electrical energy. So a rechargeable battery is an example where you get both electrical to chemical and chemical to electrical. Chemical energy to light energy. Suppose burning of a candle. Candle is a process where chemical energy is converted to light energy, some amount of heat energy also. Chemical energy to light energy. Because the objective of a candle is to provide light energy, and definitely some amount of heat energy is also produced. So chemical to light energy, this might be taken as an example. The process of photosynthesis is exactly the opposite of burning of a candle, you can say. In terms of energy conversion, it is opposite. So in the process of photosynthesis, sunlight is absorbed, and you can say that light energy is converted to chemical energy. Light energy is converted to chemical energy. Electrical to light, you will get various examples, starting from electric bulb to a CFL lamp to LED lamps. So electric bulb, CFL or compact fluorescent lamps, LED bulbs. These are examples where electrical energy is converted to light energy. These are quite common examples that we frequently encounter. Light to electrical, you can take the example of photoelectric cell, or a solar cell, where light energy is converted to electrical energy. So photoelectric cell, a specific phenomenon that is called as the photoelectric effect, is responsible for conversion of light to electrical energy. Some more examples. Sound to electrical and electrical to sound energy. Suppose you take the example of a loudspeaker, then it converts electrical energy to sound energy. On the other hand, if you take the example of a microphone, it will convert sound energy to electrical energy. Next, heat to mechanical. Heat to mechanical energy, we may not get a direct example, but indirectly I can say that in a steam engine, the chemical energy of the coal is first utilized to produce heat energy of steam, and then the steam engine can drive to produce mechanical energy. So this is an indirect conversion. Chemical energy of coal, of burning coal, to heat energy of steam, to mechanical energy of the engine, to mechanical energy of the engine that drives a locomotive. Chemical to heat energy, so many examples are there. Whenever any fuel is burned, definitely chemical energy is converted to heat energy. So burning of coal, combustion of petroleum, etc. Even the burning of wood, it converts chemical energy to heat energy. Chemical to mechanical energy, in the case of automobiles, it is the chemical energy of the petrol or diesel that changes into mechanical energy. The chemical energy of petrol or diesel converts to mechanical energy. Many such examples you will come across in your textbook. You can refer to that. Whatever energy change that we have taken examples of, no change is 100%. That means whatever device you are using or whatever process you are considering, in any example, sound to electrical, electrical to sound, chemical to heat, electrical to heat energy, heat to electrical, in whatever form of energy conversion we are trying to realize through our devices that we have created, the energy conversion is never 100%. Some amount of energy is lost. Say for example, if you are converting electrical energy to mechanical energy, some amount of energy might be lost in the form of heat. If you take the example of a bulb, its objective is to produce light energy by consumption of electrical energy, but somehow the energy is lost in the form of heat. So a considerable amount of energy is lost to the surroundings by conversion into other undesirable forms. So the energy conversion is never 100%, and whenever one form of energy, in order to get converted to another form of energy, is not possible 100%, it might get converted to some other form of energy, and that is called as energy degradation. Some amount of energy is always lost to the surroundings, or which gets converted into other undesirable forms. That is called as energy degradation. Energy changes that occur in a simple pendulum. When a simple pendulum oscillates in the absence of any medium, We assume that the simple pendulum is oscillating in vacuum and there is no air resistance to obstruct the motion of the simple pendulum. In that situation, the mechanical energy is conserved. So in a simple pendulum, mechanical energy is conserved provided the pendulum oscillates in vacuum or in the absence of any medium. This is a vital assumption whenever we consider conservation of mechanical energy. If the pendulum is oscillating in vacuum. So, mechanical energy is conserved means the kinetic and the potential energy continuously changes from one form to another as the pendulum oscillates from its mean position. So, let us consider three stages of the oscillation. Suppose the pendulum is oscillating between its two extremes, and suppose this is the mean position and these are the two extreme positions of oscillation on either side of the mean position. Suppose the point A refers to the mean position or the equilibrium position, and point B and point C they refer to the extreme position on the left hand side or the right hand side of the mean position, the two extremes. So whenever the pendulum is oscillating at its mean position, the kinetic energy is maximum. The kinetic energy is maximum and the potential energy denoted by U, this is minimum. Actually the potential energy is 0 at this position and the kinetic energy is maximum. So the entire potential energy has converted to kinetic energy whenever the pendulum passes through whenever the bob of the pendulum passes through the mean position. Its potential energy will get totally converted into kinetic energy. And whenever the bob reaches the extreme position on either side of the mean position, then at these positions B and C, the kinetic energy is minimum and it is practically 0. The minimum value is always 0. And we can say that the kinetic energy has totally converted to the potential energy which becomes maximum at the extreme positions. In this position also the kinetic energy is minimum or 0 and the potential energy is maximum. If you plot the graph where kinetic energy gets converted into potential energy and vice versa, the graph will not be a straight line like that of an object which was falling under gravity that we had previously realized. This graph is discussed in higher classes. Still, the graph will be of this nature if you consider the potential versus kinetic energy graph and the conversions. So at the mean position, the potential energy is minimum. So this will be the graph that represents the potential energy and this will be the graph that represents the kinetic energy. So this will represent kinetic energy and this graph will represent potential energy. With respect to the mean position, suppose the mean position is the point A, so this refers to the mean position. We have taken the mean position to be the origin and the motion of the pendulum is suppose plotted along the x-axis. So with respect to either extreme, as we have shown that the kinetic energy is minimum, so kinetic energy becomes minimum and the potential becomes maximum. Whereas at the mean position, the kinetic energy is maximum and the potential energy is minimum. I repeat again, at the mean position, the potential energy is minimum and the kinetic energy is maximum. At the extreme positions, on either side of the mean position, the kinetic energy is minimum whereas the potential energy is maximum. So let us take another example of a device where we can introduce the nuclear energy that gets converted into electrical energy. For example, we take the example of a nuclear reactor. In a nuclear power plant, a nuclear reactor is responsible for conversion of nuclear energy to electrical energy. Now, the nuclear reactor consists of many important parts, but all the parts are not necessary in this discussion. We will concentrate only on those parts that are in the process of conversion of nuclear energy to electrical energy. In most of the nuclear reactors, a process which is called as nuclear fission is the strategy behind conversion of nuclear energy to electrical energy. So nuclear fission is a process where a heavy element such as thorium, plutonium or uranium, such as uranium, plutonium, thorium, etc., splits into lighter nuclei. And energy is released in this process. Releases an enormous amount of energy. Amount of energy is released. So nuclear fission is the process by which nuclear energy can be converted into electrical energy. So in nuclear fission, the energy that is released is quite large as compared to conventional processes of obtaining electrical energy. For example, electrical energy can be produced in a hydroelectric power plant or in a thermal power plant, but the amount of coal required to produce the energy or the amount of water stored in a dam to produce the energy is quite small as compared to the energy that nuclear fission can produce. So nuclear fission and nuclear fusion are two standard processes, but nuclear fusion we won't discuss because still it is not being utilized for production of electrical energy. So nuclear fusion is a popular process. So whatever nuclear phenomenon occurs, in any type of nuclear phenomenon, nuclear process or nuclear phenomenon, you can say that it is the loss in mass of the nucleus that gets converted into energy. Loss in mass produces energy. If you consider a nuclear reaction, then the sum of the masses of the products and the sum of the masses of the reactants differ. The sum of the masses of the reactants is slightly greater than the sum of the masses of the products. Don't confuse with any chemical process, because here whenever we refer to mass, we are referring to the atomic mass of the element considered. So in any nuclear process, it is the loss in mass that produces energy, and the loss in mass is with respect to the mass of the nucleus, specifically because nuclear processes will involve the nucleus, and it is the loss in mass of the nucleus that produces energy. And the famous equation is E equal to delta M into C square. This is the Einstein's mass energy equivalence relationship, and this is utilized whenever we try to realize the loss in mass that produces energy. Here delta M refers to loss in mass and C refers to the velocity of light, and this produces amount of energy. So loss in mass should not be confused with the conventional mass. It is the nuclear mass. The nuclear mass of the reactants is somewhat greater than the total nuclear mass of the products in a nuclear reaction, and that loss in mass is producing some amount of energy. So in a nuclear reactor, nuclear fission of some element occurs. That heavy element that is taken in a nuclear fission, whether it is uranium or plutonium, that heavy element is called as the nuclear fuel or the fuel of the reactor. The heavy elements such as uranium, an isotope of uranium is popularly used, uranium-235. Uranium-238 is another isotope, but uranium-235 is utilized for conversion of nuclear energy to electrical energy. So that is the nuclear fuel. Now this nuclear fuel is collided with neutrons. Neutrons will collide with the nuclear fuel such as uranium, and after collision it will produce lighter nuclei. Now there are many stages of the reaction. If I take an example, I can say that suppose uranium-235 is collided with neutrons, then it produces barium and krypton, 3 more neutrons plus energy. So these are the lighter nuclei, barium and krypton. It depends upon the speed of the neutron that collides with the uranium nucleus. With respect to different speed and different reaction conditions, different type of lighter nuclei can be formed. This is just an example. Now again, these neutrons will further collide with uranium and they will produce furthermore 3 neutrons per neutron will get. That means after one stage of the reaction you are getting 9 neutrons and 3 times the energy that was reduced. So this can continue, and cumulatively this will produce enormous amount of energy, but that has to be controlled, otherwise the energy is so large that it will lead to some amount of destruction. So in order to use that energy constructively, the number of neutrons that is produced in the nuclear fission of uranium-235, that has to be absorbed. You cannot continue with 3 neutrons per reaction and that the energy will be so large that it will go out of control. So in order to control, the speed of the neutrons should be moderated, and also the number of neutrons, the excess number of neutrons has to be absorbed. So another important part of the nuclear reactor is moderator. And this moderator will actually slow down the speed of neutron, slows down the neutrons. As moderator, we use graphite, heavy water, heavy water means deuterium oxide. The conventional water is H2O and heavy water is D2O. Hydrogen has 3 isotopes, 1H1, 2H1 and 3H1. So heavy water is D2O. Hydrogen, I hope you know that it has 3 isotopes. Now this is deuterium, and from it we get D2O, which is heavy water. This is heavy water. This is used to slow down the speed of the neutrons. And in order to absorb the neutrons, that means at every stage of the fission reaction, 2 neutrons has to be absorbed, as per this example. So in order to absorb the neutrons, control rods are used. So another important part is control rod. Cadmium or boron are used as control rods, and they are used to absorb the neutrons. The excess of neutrons that are produced in every stage of the chain reaction. So this is a brief overview of the nuclear reactor. Now, the excess amount of heat that is produced that excess amount of heat is used to produce steam at a very high temperature, and steam at a high temperature is used to rotate a turbine. The turbine is connected to a coil that is rotating in a magnetic field, and that produces electrical energy. So ultimate realization of the nuclear reactor is that it has to produce some amount of excess heat energy that will produce steam at a very high temperature. That steam is used to rotate a turbine. The turbine is connected to a armature or a coil, and that rotates in a magnetic field, and we get electrical energy. The excess heat produced as a byproduct has to be cooled. The nuclear reactor has to be cooled time and again. So as coolant, you can also consider coolant. Water is used as a coolant. Water runs through different pipes, and time and again it cools the nuclear reactor. So this is a brief overview of the production of electrical energy from nuclear energy. We will take another example of solar cell, where light energy of the sun is used to produce electrical energy. So a solar cell basically consists of a semiconductor. A solar cell, it consists of a semiconductor. A semiconductor is totally different from a conducting material or a insulator. You can say that conductors and insulators are somewhere out of the discussion, because semiconductors are not totally conducting, neither they are totally insulating material. The conductivity of a semiconductor depends on temperature. Conductivity of semiconductor depends on temperature, and at low temperatures it is less conducting, and its conductivity will increase with increase in temperature. So conductivity of semiconductor, you can say, increases with increase in temperature. Increase in temperature. So a solar cell will basically consist of this type of semiconductor, and the most popular semiconductors that are utilized in the solar cell is silicon and germanium. Some compounds like gallium arsenide is also used in the solar cell. So still in elemental form, none of the semiconductors can be utilized. So some impurities definitely added to this silicon and germanium, because in pure form it is not so much conducting. So some impurities are deliberately added, and we say that the semiconductors have been doped with impurities. So these semiconductors, when they are doped with impurities, their conductivity is enhanced, and with increase in temperature, the conductivity gets more prominent. A collection of solar cell is actually a solar panel. Many solar cells together will produce what is called as a solar panel. So when sunlight falls on the solar panel during the daytime, it actually gathers a large amount of solar energy and stores, and it delivers or converts the solar energy to electrical energy, which is utilized for various purposes. But still, solar panel cells or solar panels are costly, the maintenance is high, the efficiency of conversion from sunlight to electrical energy is also low, so it is not widely used, you can say. Still, this is a very good alternative as a renewable source of energy, and so with respect to other conventional sources of electrical energy conversion, using non-renewable materials like coal, etc., that we use in thermal power plant. So these are some good alternatives. A nuclear in a reactor and a solar cell is a good alternative.